The uncertainty principle UP results from the Fourier principle. It represents the second column of our platform, signals, processes, systems. This absolute limit of nature cannot be surmounted even by the most sophisticated technological equipment. Frequency and time cannot be measured accurately at the same time, not with the most sophisticated methods. At first, however, the UP has to be proved experimentally and assessed in its implications. This is carried out by means of the following experiments. The signals shown can be generated by means of the module cut and can be made audible via the sound card. First, a periodic sinus of, for example, 256 Hz is made audible via the sound card or amplifier and loudspeaker. As expected, there is only one single tone to be heard, and the spectrum shows only one single line. But this is not ideal either, and exhibits a slight spectral uncertainty in this case. For example, only 1 second was measured instead of measuring infinitely. Now listen to the experiment. Step by step, we now restrict the length of the sinusoidal signal, which is, in this case, no longer an ideal sinus. The more the length is reduced, the more difficult it becomes to hear the original tone. No time-limited sinusoidal signal has only one frequency. An oscillation pulse of this kind, called a burst, has a frequency range which gets wider and wider as the length of the burst gets shorter. In the case of a longer burst signal, many other tones can be heard alongside the pure sinusoidal tone. The shorter the burst, the more the tone turns into a crackle. If the burst finally consists of very few, for example 2 sinus periods, the original sinusoidal tone can hardly be heard through the crackling. The spectrums on the right show more specific details. The shorter the time duration delta t of the burst, the greater the bandwidth delta f of the spectrum. At first, we must agree on what is meant by bandwidth and time duration. Here, a so-called Gaussian oscillation pulse is gradually restricted in time, set up by the formula generator. The Gauss function envelops a sinusoidal signal restricted in time, guaranteeing that the oscillation pulse begins gently and ends gently without any abrupt changes. As a result of this option selected, the spectrum occurs also as a Gauss function. It also begins and ends gently. Theoretically, every Gaussian pulse lasts infinitely long because the Gauss function reaches the limit value 0 at infinity. In spite of that, the Gaussian pulses have in each case a different time duration delta t, as well as a different bandwidth delta f. Therefore, the time duration delta t and the bandwidth delta f of a Gauss pulse must now be defined in a practical sense. If the time duration delta t and the bandwidth delta f relate to the two threshold values at which the maximum functional value has dropped to 50%, the product of delta f times delta t is roughly 1. But as the bandwidth delta f is a question of definition, an inequation is formulated which permits an estimate. And that's really all we want to achieve. With that, the uncertainty principle for time and frequency reads delta f times delta t is bigger than or equals 1, which means bandwidth multiplied with time duration has at least the absolute value 1. Sinusoidal signal and delta pulse as a limiting case of the uncertainty principle. A delta pulse in one of the two domains, that means delta t against 0 and delta f against 0, always implies an infinite extension in the complementary domain delta f against infinity and delta t against infinity. This illustration shows a sinusoidal signal means delta t against infinity. This implies delta f against 0. A one-off delta pulse, delta t against 0, produces an infinite bandwidth and delta f against infinity. Note, a one-off delta pulse contains all the frequencies with the same amplitude. This makes a delta pulse an ideal test signal from a theoretical point of view, because, see the Fourier principle, the circuit or the system is tested at the same time with all the frequencies of the same amplitude. A practical consequence of the UP is the lack of ideal filters. Filters are signal technology components which allow frequencies to pass through, conducting state region, or to be blocked, blocking state region. If only the low frequencies, up to a certain limiting frequency, are allowed to pass, this is called a low-pass filter. As we wish to demonstrate, the transition from a conducting state region to a blocking state region and vice versa must always take place with a specific uncertainty. The upper Fourier playing field shows a delta pulse in the time and frequency domain. The sum of the first 10 sinusoidal signals is also represented in the time domain. If there were an ideal rectangular low pass which led through, in this case, the first 10 sinusoidal signals, and then blocks all subsequent sinusoidal signals precisely, this cumulative curve would have to appear at the output if a delta pulse had been given as input. In the lower illustration, there is an indication that this cumulative curve reaches far into the past and the future. This would in turn mean that the output signal would have had to be started before the arrival of the D-pulse at the entrance to the filter. This contradicts the causality principle. First the cause, then the effect. Therefore, such an ideal rectangular filter cannot exist. If this delta pulse response, which is termed SI function, is restricted to the segment of 1 second represented here, and an FFT is carried out, this results in rounded or wavy low-pass characteristics. All real pulse responses are limited in time. Hence, as a result of the UP, there cannot be ideal filters with rectangular conducting state regions. Another practical problem is how to optimize frequency measurements in the case of non-periodic signals. The question now remains, how, in the case of non-periodic signals with their continuous spectrum, the frequencies contained in them can be measured as accurately as possible. As a result, the general answer is obvious. The longer we measure, the more accurately we can determine the frequency. The non-periodicity is achieved here by using a noisy signal. This noisy signal is now filtered through a high-quality low pass with a cutoff frequency of 50 Hz. This does not mean that this filter does not let anything through above 50 Hz. These frequencies are damped to a greater or lesser degree, depending on the filter quality. Here we are looking at the blocking state region above 50 Hz, beginning at 70 Hz. The lower 4 signal segments contain considerably more, or rather stronger frequency ranges in this area than the overall signal at the top. Thus, cutting out partial segments produces frequencies which were not contained in the original signal. In addition, the link between the individual segments of the signal, which have been separated arbitrarily, is lost. This may mean that information has been cut up. Information consists of certain agreed patterns, see Chapter 1, and therefore lasts a certain time. In order to capture this information in its entirety, the signal segments would have to overlap as a precaution. The long non-periodic signal here is also divided up into individual time segments. This so-called windowing is carried out by means of a time-shifted Gauss window. The partial segments thus begin and end gently. In contrast to the previous illustration, the frequency domain of the time segments is not greater than the frequency domain of the signal as a whole. This important signal technology process in the time domain is called windowing. This is intended to define cutting out in the frequency domain, which is called filtering. You are already familiar with the trick of how to make a signal segment begin and end gently by means of the Gauss function. With this time weighting, the central area of the signal segment is analyzed precisely and the peripheral areas are analyzed less precisely or not at all. The experiment shows what this solution, which is in a relative sense the best, looks like. The segments begin and end gently, thus avoiding steep transitions. Moreover, the segments overlap. This lessens the danger of losing information. On the other hand, the signal is so distorted that only the central part is fully displayed and strongly weighted. The shorter the time segment, the more uncertain the frequency band is. Near-periodic signals form the ill-defined borderline area between periodic signals, which strictly speaking do not exist, and non-periodic signals. Near-periodic signals are repeated over a given period of time in the same or a similar way. Very important examples of near-periodic signals are vocals, sound, and music. The near periodicity of all tones is illustrated by means of a short clarinet tone, 440 Hz, which means concert pitch A. In the time domain, it is possible to perceive similar events at the same distance t from each other. Use a ruler to measure and calculate the inverse value 1 over t, which is the frequency of the concert pitch A. The result ought to be the basic frequency of 440 Hz. As our ear is a Fourier analyzer, see Chapter 2, we are able to recognize the bass pitch. If you are not entirely unmusical, you can also sing this tone after it has been played. The concert pitch A of a clarinet sounds different from that of a violin. That means every instrument has its own timbre. These two tones differ in the amplitude of the overtones and not in the basic pitch. As a violin sounds sharper than a flute, there are more overtones than in the spectrum of the flute. Near-periodic signals have more or less linear-like spectrums, smudged or blurred lines, which only include integer multiples of the basic frequency. The shorter the overall length, the more blurred the lines. The next experiment shows the sound of a wine glass as a quasi-periodic signal. In the time domain, it is very difficult to detect periodicity. Only the distance between the maximum values in the right-hand half appears to be constant. On the other hand, the frequency domain displays clear lines. As you will easily realize, not all lines are integer multiples of a basic frequency. The signal is therefore not near periodic. We therefore term this type of signal quasi-periodic. The physical cause of quasi-periodic signals are, for example, the oscillations of a membrane. A wine glass is a kind of deformed membrane. Waves, so-called oscillation modes with certain wavelengths or frequencies, are formed on the membrane depending on its size and shape. These frequencies then appear in the spectrum. An analysis of this kind can be used, for example, in automation technology, in the manufacturing of glasses or roof tiles, to find defective objects, for instance those with cracks. Their spectrum differs considerably from that of an intact glass or roof tile. Tones or sounds must therefore last for a longer period of time in order to be recognized as such. For this reason, tones or sounds are near periodic or quasi-periodic.